Ok, entonces retomemos desde la última slide. Oh, I'm sorry, in English. Let's take it from the last slide we did on the last video. So we're solving a problem where we have a capillary tube. On black here, you will see the 2D representation of the tube walls. Okay, and from those tube walls, you will have a meniscus that looks like this when you play when you draw it in 2D. So the meniscus has it's drawn in blue, and it has a curvature, and that curvature is produced by the force of the surface tension that we're gonna draw in red. This force forms an angle with respect to the vertical wall of the tube. And the water column, it's sort of a cylinder that has a weight that is pulling down the water column, while the surface tension is trying to pull it up. So you have two forces here. One force that is diagonal, F, that it's diagonal with respect to the wall, and then you have the actual wall. The actual weight of that. If you look from the top, the capillary tube, you will see that the film looks like this. And the film is sort of a circle. And this circle has a perimeter. And on that perimeter is where the force is distributed. So remember, surface tension is a force distributed in a length. And in this case, this length would be the perimeter of this circle. See, I'm drawing the wall so you can see that this is actually the capillary tube. And I put in an F on all the forces that I've been drawing here. Okay, let's get back in business here. Let me draw. This force has two components. Has a component in X and a component in the Y direction. Okay. So this is the force that is diagonal. It forms an angle theta with respect to the vertical, as we see on the top. And the y component of this force, which is Fy, it's vertical, and the x component of this force is it's on the horizontal. So this is Fy, and it's equal to the F times the cosine of theta. Yeah, remember this from physics classes. And this is Fx, and it's equal to F times the sine of theta. So we're doing a free body diagram, un diagrama de cuerpo libre, and what a free body diagram does is you take out the problem from its environment and represent the environment through forces, right? Free body diagram. Now, we're gonna apply Newton here, second law of Newton, that it says that the sum of forces is equal to mass times acceleration. And since there is no velocity, there's no acceleration, the sum of forces is equal to 0, because this is a static problem. It's not moving, it's not dynamic. And which forces are applied here? They're only in the y direction, as we can see. So we have a force here, right here, and a force here. So the Fy force is pulling up while the W, or weight, is pulling down. And the sum of those forces is in equilibrium, meaning the sum of forces is equal to 0. Now, Fy, we said, is actually F cosine of theta. And that's minus W, which is the force, the weight force. And that is equal to 0. Now let's remember. Gamma is the specific weight. We saw that in the, I think it's video number 3. So the specific weight is basically the weight of the fluid divided by the volume in which this fluid is contained, right? This is the same as the density times g, where g is the acceleration of gravity divided by the volume, right? G should be redrawn here. Okay, excellent. Now, if we solve for weight, right? Weight is equal to gamma times the volume, and we know that gamma is rho times g times the volume. I mean, gamma is rho times g, and we multiply that by the volume. I'm drawing the volume with the letter V with a straight line. It looks like an inverted A, and this is because we don't want to confuse volume with velocity. So every time I use this nomenclature, a V with the line cross through it, and then I'm referring to the volume. Let's put this in a box. Okay, so we won't forget. Now let's go back to the equation number 1. So from 1, Fy is equal to W. So the force, the pulling force, it's equal to the weight. But we know that F cosine theta then would be equal to rho g volume from what we did in the square, in the rectangle above. Now let's remember something else, because we know more about the volume, because we know the shape of it, and we also know something about surface tension. We know the surface tension from the previous video is the force distributed in a length, or force over length, right? And this length would be the length holding, in which the force is distributed and holding this liquid interface, or the liquid film. And this is the force distributed on that length. As you can see here, see? This is the circumference, and this is the force distributed on that length. And we know then that the length is the perimeter of the tube circle, right? Tube perimeter. So L is equal to 2 pi r. This is the perimeter of a circle, where r is d divided by 2, where d is the diameter of this tube, the inner diameter, not the external diameter. Okay, let's call this equation number 2. Let's call this equation number 3, and let's call this equation number 4. So 3, equation 3 and 4 would be put into equation 1. So remember, F equals sigma times L if we solve for force in the surface tension equation, which is equation number 3 here. So F times L times cosine of theta from equation 1 is equal to weight, which is density times g times the volume. But we know something else. We know that L is 2 pi r because it's the perimeter of the tube. Therefore, we have a new equation just by replacing L, but with 2 pi r. Now, the volume, let's remember this. The volume of a cylinder. Let's draw a cylinder. This is the cylinder of water. That is the water that is being pulled up in this straw or capillary tube that it's immersed in the water that it's contained in another recipient, right? So this is the water surface, and then the water, it's going up to the capillary tube at a distance h, okay? And so we can actually compute this because we know that the diameter is 2r and the height is h. So remember now, how can we compute the volume of a cylinder? So the volume of a cylinder is equal to h times the surface of the cylinder, which is pi r square. And this is our fifth equation. So 5 into, we call this equation 6, and we put 5 into equation 6. So we get sigma, surface tension, times 2 pi r, which is the length, times cosine of theta is equal to rho g times the volume of the cylinder, which is h times pi r square. And there are things we can actually eliminate here. So r eliminates the r square, pi goes away, and what do we get? We get that sigma times cosine of theta, 2 sigma cosine of theta is equal to rho times g times h times r. And we want to solve for h. So let's get h alone and put everything else on the other side. Let me copy this equation to go to the next page, because we are pages now. Okay, let's paste this equation. So, if we solve for h, let's go back to black. So h equal to 2 sigma divided by rho g r times everything else times cosine of theta. And let's square this equation. This is our surface tension equation to compute the height of the column that is moving up or down depending on the fluid. So this is the surface tension equation that we're going to use to solve our queries. Data from problem A, we will use water, and in B we are gonna use mercury. So the sigma for water is 0.0728 newtons per meter, as we know from the original problem. The density or specific mass, it's around 1000 newtons per meter cubed. Let's write it again. Kilograms, I'm sorry. This is not specific weight, it's specific mass or density, kilograms per cubic meter. And G, which is the acceleration of gravity, would be 9.81 meters per square second. And R is the diameter. We have three diameters that we're looking at. Okay, R, the first R is 5 millimeters, right? 5 millimeters is the diameter, and the radius would be 2.5 millimeters. And we want these 5 millimeters expressed in meters because every single equation we're using, see, it's using meters. So we want to be consistent with the units. So 2.5, we don't want to use commas, it's British writing. So 2.5 millimeters is X, and 1,000 millimeters is 1 meter. So we do a rule of 3, and we say 2.5 times 10 to the minus 3 meters. So this is how we find the conversion of units from millimeters to meters. Okay, the height for a diameter of 5 millimeters would be, if we follow the equation above, is 2 times sigma, which is 0.0728 newtons per meter, divided by rho gr. Rho is 1,000 kilograms per cubic meter, times g, which is 9.81 meters per square second, times r, which is 2.5, divided by 1,000. Let's write it as we did before. 2.5 times 10 to the minus 3 meters. And this is all multiplied by the cosine of theta. And theta for water, it's the angle of the contact angle of the water meniscus, which is 20 degrees. And this is taken out of, for this temperature and this kind of fluid, this is done in experiments. And it's in tables. So if we solve for this, remember to write all the units, just as in physics. Don't ever forget to write the units, because you have to be consistent with the units. Okay, 2 times 0.0728 divided by 1,000 divided by 9.81 divided by 2.5 times 10 to the minus 3 times everything times cosine of 20 degrees. Remember, your calculator has to be in degrees and not in radians. This is a common mistake. We don't want to make that mistake. Not even here. Even worse if you do it in the test. So be careful with this. I'm computing on my calculator, on my phone actually. So give me a second. So I'm going to write it down here. So H5 for water would be 0.005. Again, I'm writing a comma. I'm sorry. It should be a point, a dot. So 0.0056 meters, which is exactly 5.6 millimeters. Now, if we do the same for 10, let me just do a rapid computation. So this is H10, or the height for a diameter, for a tube diameter of 10 millimeters. So see, we're changing every time the diameter, and when we have a bigger diameter, the height that the capillarity do is different. So 5.6 here and 2.8 millimeters. So for a diameter of 5 millimeters, which is a very thin tube, we have 5.6 millimeters. For a diameter bigger than double the other one is 2.8 millimeters height. So you rise less water when you have a wider capillary tube. And finally, when we try H20, which has a radius of 10 millimeters, you get a rise in the water column of 1.4 millimeters. See, as you can see, as we widen or get a wider tube, as we increase the diameter of the capillary tube, we decrease the height or the effect of surface tension on the rise of the water. So as we increase the diameter of the capillary tube, we cause a decrease on the rise of the water column. So H goes down. Now, let's draw a line and do the same calculations using the same equation, H equal to 2 sigma divided by rho GR times cosine of theta. Let's copy this and put it down. We're going to do this now, and we're going to do the computation for the 3 different diameters, but now for mercury. Mercury. This is letter B on the problem. And H is equal to 2 times 0. I'm using the equation above. 0.466 newtons per meter. This is the value of surface tension at a given temperature for mercury. Divided by rho G, which is 13,000, which is rho, times 9.81, which is G, and that gives us, and the 13,000 is in kilograms per cubic meter, and 9.1 is meters per square second. And so we get finally 127,000. Let's erase the dot, it's a comma. 127,530 newtons per cubic meter, which is the specific weight of the mercury. We write this down. We keep track of the units. Don't ever forget that. If you don't do it in the tests, you're gonna get less points, right? Even though you have the right answer, you have to keep track of the units. You have to write them down. So this is times 2.5 to the minus 3. So meters goes with meters. This gets squared. This meter over here. Goes with this meter. Newtons go with newtons. And we multiply everything by cosine of 130. So 130 is the angle of contact with the vertical wall that mercury forms when it shapes a meniscus. And I'm computing here 2 times 0.466 divided by 127,530 divided by 2.5 to the minus 3 times the cosine of 130. So you know that the cosine of 130 is negative and is minus 0.64, and the cosine of every angle that is bigger than 90, it's negative. Between 90 and 180, it's negative. Remember that. So every time you get an angle of contact that it's greater than 90, you will have a negative number. And this means cohesion is much bigger than adhesion. And what causes actually is the reduction, or the water's not rising but going down. So the H5 is equal to minus 0.002 meters, which is basically minus 2 millimeters. For H10, we do the same calculation, but using the radius 5 millimeters for the diameter of 10, and we get minus 0.95 millimeters. This is almost, it's a very small h. And for 20 millimeters of diameter, which is actually 10 millimeters in radius, we get a negative 0.018, I think. Oh, I'm sorry. Minus 0.47 millimeters. Now, Conclusion. Let me put this in a box. Let me fix the box so it looks nicer. So, same way, the effect of D, when you increase the diameter of the capillary tube, there is a decrease of the effect of the surface tension, and therefore H decreases. Okay? And between water and mercury, you see that because of the angle of contact, when you have angles that are less than 90, it means that cohesion is less important than adhesion, and therefore column goes up, which is the case of water. When the angle is bigger than 90, then like mercury, the column goes down under the interface or the water surface, because the cohesion is much bigger than adhesion, so you go down. So this is the case for water, so the water makes it go up, while in mercury this goes down from the water surface. And that would be all, and this is due to the cosine and the negative answer for the cosine of 130. Well, we're done. Thank you. Last video of this unit.